let us see what are the different types of unit cell. The first one is the simple cubic unit cell called SCC. Now, this is the structure of a simple cubic unit cell. That is, we have atoms placed on the 8 corners of a cube. Here, the atoms will be in contact with each other. The atoms at the edges will be touching each other. Now let us see how to draw the simple cubic unit cell. First, we need to learn how to draw a cube. For that, we draw a square. We place another square in front of it, and the edges are matched. Now we place atoms at all the edges. Here, 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 here. We have filled atoms on the top face. And here we have filled atoms on the bottom face. So we have placed 8 atoms at the 8 corners of a cube. And this gives the simple cubic unit cell. Now, the total number of atoms per unit cell is given as such. That is, each of the atom placed at the corner will be shared with 8 different unit cells neighboring it. Hence, if we take this particular unit cell, only 1/8 of it is contributing to this unit cell. Likewise, we have 8 different atoms in this single unit cell. Hence, 8 atoms, each contributing only 1/8 of its fraction to it, gives 1/8 into 8, that is 1. Hence, this unit cell has number of atoms per unit cell as 1. Now the next type of unit cell is the body-centered unit cell BCC. This is the structure of the body-centered unit cell. Here, the atoms along the diagonal will be touching each other. That is, we have 8 corner atoms and a single atom placed at the body center of that unit cell. And the body center atom will be touching the corner atoms. Now to draw that, first we draw a square, then another one in front of it. We match the edges. We place atoms at the corners, 8 corners. And finally, we place a body-centered atom. Now, the effective number of atoms per unit cell is the atoms at 8 corners contributing 1/8 of its fraction to it, plus the body-centered atom that is contributing wholly into that unit cell. So, the number of atoms per unit cell is 2. The next type of unit cell is the face-centered unit cell FCC. This is the structure of the face-centered unit cell. We have 8 corner atoms and an atom placed at the center of all the faces of the cube. Here, the face-centered atoms will be in contact with the corner atoms. Now to draw it, first we need to draw a square, then another square in front of it. Then we match the edges. Then we place 8 corner atoms. And then we place the face center atoms. We have an atom at the center of this face, another atom at the center of this face, another atom at the center of this face, and another atom at the center of this face. For a cube, we have 6 faces. So here at the top face, another atom at its center, and the bottom face, another atom. Hence, we have 6 face center atoms. So the total number of atoms per unit cell is, we have the corner atoms given by 1 by 8 into 8 plus the contribution of face center atoms is each face center atom is shared by 2 unit cells. That is, this face center atom contributes only half of its fraction to this unit cell. Okay, so we get 1 by 2 into 6 number of face center atoms, and this will give 1 plus 3, that is equal to 4. Now the next type of unit cell is the hexagonal close packed unit cell, HCP. It is distributed as such in this figure. Here we have the bottom layer stacked as the A, then the second layer showing B stacked. Then again we have the stacking similar to this one, hence again A, then B, A, B, A. So when atoms are arranged in A, B, A, B, A, B stacking, they will have the hexagonal close packed structure. Now to draw it, let us draw a hexagon on the top and another hexagon on the bottom, and we shall match the edges by drawing straight lines. On all the corners, let us place atoms. So here we place an atom. We have 6 atoms on the top hexagonal plane, and at the center of it we have another atom. On the bottom again, 6 atoms on the corners of the hexagon and another atom at the center, and we have 3 other atoms at the center between the 2 hexagons. These 3 atoms will be placed in the voids of these atoms in the hexagonal planes. That is, if we divide this hexagon into different quadrants, we have this quadrant, and at the center we place this atom. Then we leave the next quadrant, we take the next quadrant, and on the center we place this. We leave this quadrant, and on the next quadrant we place this atom. Okay. Now here the number of atoms is calculated as, let us take the 6 corner atoms on the hexagon. We have 2 hexagons, so 2 into each of these atoms on the hexagon contribute to 6 other surrounding hexagons. Okay, so only 1 by 6 of this atom is contributed to this unit cell. So we have 1 by 6 into 6 atoms on one hexagonal plane, plus the center atom of that hexagonal plane will contribute to only 2 unit cells. Only half of its fraction is shared in this single unit cell. So we have 2 such atoms, that is 2 into 1 by 2. Plus we have 3 atoms that are wholly contributing into this unit cell, that is 3. Hence we get the number of atoms per unit cell as 6. Now, coordination number is defined as the number of equidistant nearest neighbors that an atom has in the given structure. It is of importance that we know that it is the number of equidistant nearest neighbors. Okay. Here we have 4 different simple cubic unit cells stacked together. And if we take this atom here and count the number of equidistant nearest neighbors, we get its coordination number. That is shown here: 1, 2, 3, 4, 5, and 6. So the coordination number of this simple cubic unit cell is 6. For the body-centered cubic cell, the coordination number is 1, 2, 3, 4, 5, 6, 7, 8. Okay. In the face-centered unit cell, the number of equidistant nearest neighbors can be counted as, here we have taken 2 nearby unit cells Only then we shall get the whole nearest neighbors. So along this plane, we have 1, 2, 3, 4, and along this plane we have 5, 6, 7, 8, and along this plane we have 9, 10, 11, 12. You should try to visualize it. So the coordination number for FCC unit cell is 12. Now in the hexagonal close packed unit cell, the coordination number can be counted as, we have the center atom on one of the hexagonal planes, and the surrounding 6 atoms is first counted, that is 1, 2, 3, 4, 5, 6. Then this atom again is in contact with the 3 atoms of the above unit cell and the 3 atoms within its unit cell. So we have 7, 8, 9, and 10, 11, 12. Here coordination number is 12. Now another parameter in this crystal structure is the nearest neighbor distance. It is the distance between the centers of 2 nearest neighboring atoms. So if 2 atoms are touching each other, the distance between the centers of these 2 atoms will be 2r. Hence nearest neighbor distance is 2 times the radius of that atom, 2r. In the simple cubic unit cell, the nearest neighbor distance 2r will be equal to the lattice parameter A itself. These 2 atoms, it will be touching each other. Hence, we can write 2r is equal to the lattice constant A. In body-centered unit cell, the body-center atom will be touching these corner atoms. And we can draw a line between these, diagonal line can be drawn between the corner atom and the body center towards the other corner atom. So here we get a relation between the nearest neighbor distance and the lattice constant as 4 times r. So we have 1r, then 2r, again 1r. So 4 times r is equal to this body diagonal. That will be equal to root 3 times A. So the diagonal along this face, it will be obtained as square root of the A square plus A square. That is root 2A. Again, the body diagonal is taken as the square root of 2A square plus A square. That is root 3A. Hence, we get 4r is equal to root 3a. Now, in the face-centered unit cell, now the face center atom is in contact with the corner atoms. So, we can draw a diagonal on any face and get a relation between 2r and a. So, here in FCC, we have root 2 times a is equal to 4r. That is r plus 2r plus r. That is 4r is equal to the space diagonal root 2a. In hexagonal close packed unit cell, the nearest neighbor distance is given as 2r is equal to a. That is, here we can see that the corner atoms on the hexagonal plane, they are touching each other, right? Hence, 2r is equal to the lattice constant A. Now, atomic packing factor or APF defines the packing capacity of atoms within that structure. So, it is the fraction of space occupied by the atoms in a unit cell. In other words, we can state atomic packing factor as the ratio of volume of atoms occupying in the unit cell to volume of the whole unit cell. So in simple cubic unit cell, the atomic packing factor is ratio of volume of atoms in the unit cell. So in the unit cell, we have number of atoms is 1, and the atom has a spherical shape, hence 4 by 3 pi r cube. So the volume of atoms in the unit cell is 1 into 4 by 3 pi r. And the ratio is to the volume of the unit cell, that is A cube. Now we substitute here A in terms of the nearest neighbor distance. So in simple cubic unit cell, we have 2R is equal to A. So substituting that, we get pi by 6, that is 0.52. 52% of the unit cell is occupied. This shows that simple cubic unit cell has a loosely packed structure. Only half of the unit cell is occupied by the atoms. Likewise, if we do the calculations in the body-centered unit cell, we find that the atomic packing factor is equal to volume of atoms in the unit cell is given as number of atoms in that unit cell is 2 into 4 by 3 pi r cube divided by volume of that unit cell is A cube. Substituting here using the relation root 3A is equal to 4R, we get root 3 pi by 8, that is equal to 0.68. That is 68% of that unit cell is occupied. Hence we say body-centered cubic unit cell has a closely packed structure. In the face-centered unit cell, the atomic packing factor is calculated as ratio of the volume of atoms in the unit cell, that is number of atoms is 4 in a unit cell into 4 by 3 pi r cube divided by volume of the unit cell A cube. Here A is substituted using the relation 4R is equal to root 2A. Hence we get root 2 pi by 6, that is 0.74. That is 74% of the unit cell is occupied by the atoms. From this we understand that the face-centered unit cell has the closest packed structure. Again, in hexagonal close packed unit cell, atomic packing factor is calculated as the volume of atoms in the unit cell, that is, there are 6 atoms per unit cell, hence 6 into 4 by 3 pi r cube divided by the volume of the unit cell. The volume of the hexagonal unit cell is 3 root 3 by 2 A square C, where C is the length of that hexagon. Okay. Hence we substituting the values for A using the relation 4. Now substituting for A using the relation 2R is equal to A, we get 2 pi by 3 root 3, the whole into A by C. Now from this structure, we have the calculation that A by C is equal to root 3 by 8. So substituting that, we get 0.74. That is again 74% of the unit cell is occupied by the atoms. So HCP also has the closest packed structure. Now, comparing these different unit cells, we have the simple cubic unit cell shown as such, the body-centered cubic unit cell shown as such, face-centered cubic unit cell shown as such, and the hexagonal close packed unit cell shown as such. The number of atoms here is 1 for the simple cubic, 2 in the body-centered, 4 in the face-centered, and 6 in the hexagonal close packed unit cell. Coordination number is 6 for the simple cubic, 8 for body-centered unit cell, 12 for the face-centered unit cell, and 12 again for hexagonal close packed unit cell. Atomic packing factor is the least for simple cubic, and hence it is loosely packed. Body-centered has an atomic packing factor of 68%. It is close packed. And face-centered cubic and hexagonal close packed structure has the highest atomic packing factor, that is 74%. And we have examples for materials showing different structures of unit cells. Polonium is the only element that shows the simple cubic unit cell at a particular temperature. Then body-centered cubic unit cell structure is shown by sodium. Face-centered cubic unit cell structure is shown by silver. And hexagonal close packed unit cell structure is shown by zinc. That's all for today's session. Thank you.